to the Earth Day Virtual Stage and Festival. For those of you just tuning in, my name is Ingrid Paredes, and I am the co-chair of March for Science New York City, and also a PhD candidate in chemical engineering at the NYU Tangent School of Engineering. If you're just tuning in, we're doing the technology and infrastructure segment right now. And what this means is we're talking about everything from new infrastructure, sustainable food, and now we're turning the conversation to decarbonizing our processes. In the last segment, we just heard from experts talking about modernizing and building resiliency into our electrical grid. And now we're turning to two experts, two chemical engineers based in New York City, Dr. Miguel Modestino from the NYU Tangent School of Engineering, and Dr. Alissa Park from Columbia University, professor at Columbia University, to talk about how we can modernize our chemical processes. So welcome to the virtual stage to the both of you. Yeah,
nice to meet you.
It's really, really nice to have you both here. So I'm going to start with Miguel, and we're going to have a conversation over the next 15 minutes about what it is going on with our industrial processes and what we can do about emissions, both from a manufacturing standpoint and also about the emissions that are inherently in these chemical processes that we can't deal with. So Miguel, I'm going to start with you. So the chemical industry, for those of you who don't know, is one of the biggest CO2 emitters worldwide, right? This is how we get and basically process raw materials to produce consumer products like food, clothing, pharmaceuticals. And these are necessary processes, but it doesn't necessarily mean that we can't innovate and push them further. And this is something that in your work, you've really been looking at because electrochemistry has the potential to change. So for those of you who haven't heard about electrochemistry, can you give a brief introduction? How can we tackle emissions chemical processes and where do they come from?
Yeah, sure. Thanks a lot, Ingrid. So perhaps I'll start with the first question. What is electrochemistry, and how is that different than what we do today? So if you look at the big majority, like 97% of our chemical processes in industry, they're what are called thermochemical processes. So these are processes where you use heat to do a chemical reaction. And usually that heat comes from combustion of fossil fuels. And this is because of historical reasons, right? Like the chemical industry sort of grew with the oil industry, and you have these resources that serves as your feedstocks to make the chemicals that we need, at the same time that they serve as your energy feedstocks to provide the heat to transform those chemicals. What electrochemistry does is it allows you to integrate directly electricity into chemical reactions. So instead of using heat, you would use electricity. And why is this a route towards decarbonization? Well, the reason is because if you use electricity directly, you could source this electricity from clean energy, like solar cells or windmills or whatnot. And in this way, you sort of move the problem from a chemical plant where you're using combustion to provide the heat to these units to the challenge of now decarbonizing the grid, which is still a challenge, but we do have technology that would allow us to do that.
Yes, that's really exciting. It sounds like a potential to really clean up the processes from basically like start to finish. So where's the technology at now? What kind of reactions have we looked at with electrochemistry?
Yeah, so because of the same historical reasons that I mentioned, there is really not much electrochemistry used in the chemical industry. There is a few processes, right? Like so we make all of our chlorine, like bleach and chloride that is used in the industry using electrochemistry, basically taking salt water where you have NaCl, and then that Cl that is dissolved in the sea becomes chlorine, like via electrolysis. That's one of the largest processes, so it uses close to 2% of all electricity in the world just to make that chemical. Another process that is electrochemical is aluminum production, where you basically mine alumina and then you apply electricity and then you get metallic aluminum. And again, that's another process that takes about 2% of all electricity in the world. But when you think about the chemical industry, these are sort of like niche processes. They look very different than your typical like chemical reactors that if you have driven through a petrochemical plant or a refinery, you usually see, like, with like those like fumes coming from the top and whatnot. So in those petrochemical plants is where the bulk chemical processes happen, and that's where the majority of the emissions come from. And these processes are processes in which you take oil, petroleum, or natural gas, and then you transform it into other molecules that contain carbon. So these are organic molecules, right? And in organic chemical production, which is the big majority of the chemical production of the industry, there's only one process that uses electrochemistry to produce 30% of this small molecule that is used to produce nylon, which we have been looking into it. And the reason why that's the only process is because these are processes in which we don't train chemical engineers to design. We train chemical engineers to design thermochemical processes because that's what the industry evolved, and there is not much knowledge on how to transform processes that are run thermochemically into processes that are run electrochemically.
So where does the chemical engineer start then to make this transition? Like, what are the outstanding challenges that need to be addressed to really scale this up?
Yeah, so the thing is a twofold challenge. You know, there is an economic challenge and there is a technical challenges. We have some technology that will allow you to produce some of the chemicals, not all of the chemicals used in electrochemistry directly. The challenges come from basically the economic challenges come from two sources. One, energy is sourced from fossil fuels. We know it's cheap, it's inexpensive. So there is very little incentive to transition that heat that you source from oil that you have available in your refinery and whatnot, your fuels, to electricity, which today is more expensive than using fossil fuels to drive this process. The second one is the capital expenses of the plants themselves. And this is a challenge that I believe is surmountable, and it has to do with scale. Since we know how to manufacture and implement like distillation columns or packed bed reactors, which are like sort of typical chemical reactors that you find in a refinery, you can like literally go into Alibaba and like buy them off the shelves. That doesn't exist for electrochemistry. So basically every single electrochemical process that you see implemented in industry, which are very few, it's an exception in and of itself. So there's a lot of R&D that goes into developing these processes. So for us to be able to carry out this transition, we're going to have to develop this sort of like general design rules so that it becomes mainstream. And to do that, we of course have to teach our students to be able to design these reactors and think about processes in a slightly different way.
Yeah, so fun basic science research is what we're trying to say. That's really exciting. Yeah, thanks so much, Miguel. And then for processes that we can't decarbonize, like Miguel had mentioned, right, this is kind of like a novelty, and there are a few chemical processes right now that we can tackle electrochemically. What can we do about emissions that are maybe, I saw, Alissa, in a talk that you had mentioned, like past, present, and future emissions through these negative emissions technologies. So what are some ways that we can mitigate emissions that are currently existing right now?
Is it a question to me or Miguel?
Yes. Yes.
Now we are transitioning. Good.
Yeah.
So I think it's a great question about the negative emission technology. But when you talk about negative, there's a positive, right? So what we've done so far is a positive emission of the carbon dioxide or carbon. And that's when we put whatever carbon was in the Earth system and doing some process to extract energy or materials and putting it into atmosphere. That's the positive direction. So the fact that we want to do negative emission means that we are taking some carbon in the atmosphere into the Earth system so that it doesn't stay in the atmosphere. But before getting to the negative emission, we had to go through, or we are still going through, zero emission. So if you say there's something we are emitting positively, we want to stop at the zero emission first, which is a kind of putting something at the chimney or emission point, and then maybe go to negative. But there is a lot of discussion that maybe we're past the point that we should do it all, which I totally agree. That's why we are doing zero emission at the same time as negative emission. I think it's quite interesting. So obviously, negative emission technology is harder because we are going through environment to capture CO2. So let me share with you one picture. This is a report by National Academies published in 2019, one of the recent ones, on what are the possible negative emission technologies. Basically, in order to be negative, we need to go back into the history to pick up the carbon dioxide. Interesting, right? So that all the things emitted exist in the nature, quite a lot of the fraction of this carbon dioxide in the atmosphere. So any technology take the atmospheric CO2 and the very dilute concentration of about 400 to 400 ppm, and then capture it, and then somehow putting it back into the soil or putting more into the ocean, which are the largest sink of carbon dioxide, that is qualified as a negative emission technologies. But any of these technologies require energy to do a lot of process. So that if that energy can come from low carbon or carbon-free energy, that's the best direction to go. So there's a lot of people looking into different ways of doing negative emission technologies. You can go through biological pathway because plants are doing really great job doing capturing CO2 from air, and then we can extract the energy if you want to, or without, you can putting it back to the land, then that qualifies as one of the negative emission technologies. So these are the concepts that people are working on these days.
That's really exciting. What are some of the requirements to do this carbon capture then?
So let me see whether I can share with you. So carbon capture, when you think about it, carbon dioxide is called acidic gas. I think one of the things you may heard of in the past is acidic rain, right? Acid rain.
Mhm.
And acid rain is because of sulfur dioxide. Sulfur dioxide is a stronger acidic gas compared to CO2, but they're very similar. So that what happens is if you emit CO2 in the atmosphere, that's acidic gas, in order to capture acid, you need base. So if you have a basing material, you can do acid-base reaction to capture CO2. But one of the things you have to remember is that any material, it could be solid, it could be liquid, capturing carbon dioxide, you're not going to use once and throw it away, right? Because every material you made has carbon footprint and environmental footprint, which means that a lot of these environmental control technologies, including carbon capture, is a catch and release in a sense, right? You have to capture it from dilute system and then release it, something we can either sequester or do something with. So in terms of energy well, during the capture is usually downhill. And then the energy actual penalty you need to provide for overall carbon capture technologies during the regeneration. When you release that CO2 to the form, whether either we can store or use. So that energy we want to be minimized, but if that energy is minimized, means the capture energy, binding energy is also minimum, means that it will be challenged. So it's a kind of optimization between, it has to be strong enough to capture, but not too strong so that you don't put too much energy to release. But one of the challenge is that this technology is very large in scale. And as Miguel mentioned, that these things are integrated into large power systems or power plants or chemical plants. So the reactor itself is really, really large. As you can see here, this is the one system, not even full scale, but large scale demonstration in Houston area. So these two reactors are capturing and capture CO2 and regenerate the solvent in the system, so that how to scale up the materials we develop at the university or research labs to that scale takes decades. So we still have a lot of challenge how to do it effectively. We need to do a lot more demonstrations before we can really deploy this in the large scale, in commercial scale.
That's really exciting. I think we are almost at time, but I do just have one more question. So it seems like there are lots of rooms for, like, lots of opportunities for research and development in these two really exciting areas and have a lot of potential. But a lot of times people are talking about like what we can do right now. And I think that starts to have the conversations of like, you know, this technology is like what we need to prioritize. This technology is what to prioritize. And then you start to pit against each other. Different avenues, but all trying to solve the same issue. What are some ways, if either of you have any thoughts about how we can bring electrochemical processes and negative emission technologies, carbon capture together?
So for me, I think it's not only near term, but I would like to say this is not short diet. It's change of the lifestyle. So we really need to think about how we're gonna live without, like if you wanna do carbon management for the future, the best thing to do is do not take fossil carbon out of the ground, period. We want to put it back, not taking anything positive direction, which means that if you look around your room, it'll be very difficult for you to find anything does not have carbon in it, right? Which means that where are we going to get that carbon if we cannot use fossil carbon? Because we've been using all these fossil carbon, like Miguel said, right? Means that we have to go to either sky to get atmospheric CO2, which biomass does, but we can also grab it by using direct air capture technology. Another way is we can go to water, which is ocean. So ocean and sky will be the two sources for carbon, which is non-fossil. So we can defossilize, right? Not decarbonize, defossilize the chemicals and materials and fuel sector, but without renewable energy, we cannot do it. But interesting thing is, as Miguel said, fossil energy or fossil resources are usually heat. That's what we used. But now renewable energy is usually in the form of electrons. So how are we going to rebuild our entire carbon bearing infrastructure and chemical and materials industry using renewable energy, which is non-carbon based, and with the carbon, which is non-fossil, and then create the next 100 years of how we're going to live and sustaining all the materials and chemical sector? That will be a big challenge for your generation for sure. A lot of challenges, but it's also interesting because there are challenges, I believe.
Yeah. Opportunities, definitely. Yeah. Miguel, did you have anything to add?
Yeah, I mean, I couldn't agree more with Alissa on the fact that we need to have a complete life change. It's not a diet. And we shouldn't focus on short-term goals and miss the long-term goal. I mean, I think we need to very aggressively move to develop and deploy technologies that will get us to zero carbon with a combination, because there are things that we're going to be able to eliminate the emissions, and there are things that we're not going to be able to eliminate the emissions because we don't have the technology solutions. So we're going to have to capture it. But we need to move in that direction. And I think the biggest gap that we need to solve is how to move technologies where the science exists and some early demonstrations exist from the lab all the way up to deployment. And that gap in the middle, which usually referred to as technology readiness level between 2 to 5, which is like, it's too late for like academic researchers like ourselves to do it, and it's too early for companies to deploy it at large scale. It's a very deep valley of funding that is missing there. And there's no incentives for industry to invest here because there's a lot of risk. So here is, I think, where government can really come and make a very substantial difference. But we're talking about increasing the investment into clean tech, R&D, by a factor of 10 at least, to be able to get these technologies off the ground and get to points in which they can be deployed. So there's not an easy solution, you know, like, and I think we should just get out of this mindset. It's like, what can we do with what we have right now? We cannot solve the problem with what we're investing right now. We need to change the way that we think and drastically and very aggressively move towards that direction.
Yeah, I couldn't agree with both of you more. It was so nice talking to you. Unfortunately, we are out of time, but as you guys heard, we have solutions, we need to invest in them, and we need to really think about how we can really innovate and engineer a better and more sustainable world. Okay, so with that, I'll let you guys both go. I'll talk to you soon.